A model says it has a 1 million token context window. That is roughly 1,000 pages, a whole stack of books, all held in mind at once. So you build a tool on top of it. You feed it the entire contract, the whole code base, the full case file, and you ask one careful question. And every so often it answers as if a fact buried on page 400 simply was not there. It did not refuse. It did not flag that it was unsure. It just quietly left that fact out and answered as if it had read everything. For a while, that was the open secret of long context. The advertised number was real, but the usable number behind it was smaller, sometimes far smaller. People started saying a thing that sounds like an insult but was really a diagnosis. Your million-token model is lying to you. Today, 2 questions. Why was that true? And what changed by 2026? To understand the lie, you have to understand how a model even knows the order of your words. In Season 1, we said attention lets every token look at every other token, but raw attention is order blind. To it, the cat chased the dog and the dog chased the cat are the same bag of words. So the model needs a way to stamp position into each token, a step called positional encoding. Early models did it by adding a separate position signal onto each token. But the method almost every modern model now uses is cleverer, and it is the whole key to this episode. It is called rotary position embedding or rope, and it does not add a position. It rotates one in. Picture each token's query and key as the hands of a clock, several hands, some spinning fast and some slow. The further along in the text a token sits, the more each of its hands is rotated, a little for position 1, more for position 2, and so on. Now here is the trick. When attention compares a query at one position against a key at another, what it actually responds to is the angle between them. And that angle depends only on how far apart they are in the text, not on where either one started. So the same gap always feels the same, whether it falls near the beginning or far into a long document. Position became rotation, and distance became an angle. So why does the lie happen? Because the model only ever practiced those rotations up to a certain length. Say it was trained on text up to a few thousand tokens. Within that range, the hand sweep angles it has seen 1,000,000 times and handles fluently. But push past it, ask for position 50,000 when it only trained to 8,000, and you are asking the hands to sweep into angles they never once practiced. The model extrapolates and it stumbles. So engineers found a clever fix. Instead of forcing the hands into wild new angles, respace the ticks on the clock so that a much longer text still folds back into angles the model already knows. The simplest version, called position interpolation, just squeezes all the positions closer together so they fit inside the trained range. The one most self-hosters actually use is called yarn, which is smarter about it. It rescales the different clock hands by different amounts, the fast hands and the slow hands treated differently, so fine local detail and broad long-range structure both survive the stretch. And this is not abstract. If you download an open model and want a longer window, you edit a few lines in its config, a setting often called rope scaling, a factor, a base length. That single knob is you, reaching in and respacing the clock. It is not free. Stretch too far and reliability thins. But it is how an 8,000 token model grows into 128,000 token one. There is a second pressure, and it is about cost, not just angles. Full attention has every token look at every other token, so the work grows with the square of the length. Double the text, quadruple the comparisons. At 1,000,000 tokens, that is brutal. So a common trick is to let each token look only at a window of its recent neighbors, the last few thousand tokens instead of the entire history. This is called sliding window or local attention, and it makes long sequences affordable. But notice the quiet cost. If a token can only see its recent neighbors, then a fact a long way back is not something it directly looks at anymore. Information has to hop, neighbor to neighbor, to travel a long distance, and some of it gets lost on the way. So most models do not go all local. They interleave. A few layers keep the expensive global view that can reach all the way back, while most layers stay cheap and local. It is a budget. And like any budget, it leaves some long-range connections weaker than the brochure suggests. Now we can name the lie precisely. The advertised window is how many tokens you are allowed to paste in. The effective window is how many tokens the model can actually use reliably. For years, those two numbers were not the same and the gap could be large. Researchers built honest tests for this. The classic one is called needle in a haystack. It hides a single sentence, a needle deep inside a giant haystack of text, and asks the model to find it. A harder version makes the needle a paraphrase, so the answer does not share the exact words of the question, which forces the model to match on meaning, not just copy a string. And the results, around 2024 and 2025, were sobering. Models that advertised 100,000 or more tokens often held up well for only a fraction of that. In one careful study of that paraphrase case, a frontier model with a generous advertised window stayed reliable only to around 8,000 tokens. Finding a single literal needle, the easy case, got mostly solved. But connecting many scattered needles, or matching on meaning across a long distance, the cases that matter for real documents, kept sagging the further apart those facts sat. The brochure number was real. The usable number lived behind it. And here is where it would be easy to be lazy and just say AI cannot do long context. That would be wrong, because 2026 already moved. Watch the labs report on their own models in their own numbers. Take a recent frontier model marketed at a 1 million token window. On a demanding long context test, the kind that hides several needles and asks for all of them, by its own published figures it scored around 85% at 128,000 tokens, which is genuinely strong. But push that same model out to the full 1 million, and its score on that test fell to around 26%. Here is the part that matters most. A different frontier lab on a similar test at that same 1 million tokens reported roughly 76%. Same length, very different result. So the cliff is not a law of physics. It is a property of a particular model, and it moves as the engineering improves. The honest picture in 2026 is not, it cannot do this. It is, it does a lot, and it still weakens as you stretch it to the very edge of the advertised number, by a different amount for each model. Effective context today is often something like 60 to 70% of advertised, not the small sliver it used to be. Finding a single fact is largely solved now. The hard case, reasoning across many facts spread across the whole window, is where the honest gap still lives. So the past tense matters. Your million token model was lying to you in 2024. Today, mostly, it is not, until you push it to the very brink, and then it just gets quieter than it should. But there is a deeper reason long context is hard, and a whole different idea trying to fix it. Remember, sliding window was about cost. Here is the cost in its rawest form. To attend back over everything, a transformer keeps a running cache of every token it has already seen, called the key value cache. The longer the conversation, the bigger that cache grows, more memory, more work, every single step. It is like taking a fresh photograph of the entire transcript before reading each new word. So researchers asked, what if the model did not keep the whole transcript at all? What if it kept a small, fixed-sized box of running notes, and as each new token arrives it just updates the notes and throws the raw token away? That is the idea behind state space models, and the most famous of them is called Mamba. Its memory does not grow with length at all. The cost per token is flat, whether you are at token 10 or token 10 million, but the trade is real. A fixed box of notes has to compress the past, so it can blur the exact wording of something far back, and precise lookup gets harder. That is why most serious designs are hybrids, mostly the cheap fixed memory, with a few real attention layers kept in for sharp, exact recall. In 2026, this went mainstream. Several major open models shipped built this way, mixing a handful of attention layers into mostly fixed memory ones. And then, tellingly, one prominent model that had been built on this kind of efficient memory reversed course on its next version and went back to plain full attention, saying the shortcut still cost it too much on hard multi-step reasoning. So this is not a settled fight with a winner. It is the live argument over what a model's memory should even be. So put it all together. A model knows word order because position is baked in as rotation, clock hands whose angle encodes distance. The big advertised window is that same rotation, stretched past what the model trained on, propped up by tricks like yarn and sliding window, which is exactly why advertised used to run so far ahead of usable. The honest tests expose that gap, single facts easy, many scattered facts hard. And 2026 narrowed it, with labs reporting strong scores deep into the window and only fading at the very edge, while a rival idea, fixed size memory instead of a forever growing cache, fights to change the economics entirely. So the practical lesson is not fear the big number. It is respect the difference between what you can paste in and what the model can reason over, put the facts that matter where it looks hardest, and never assume a buried detail was read just because it fit. The window is real. The attention inside it is the thing to earn, and so far we have only filled that window with words. Next time, we ask what happens when you feed it a picture instead. How a model sees, and why a single image can quietly eat thousands of the tokens we just fought so hard to protect.